Hi, good morning everybody. My name is Claire Walsh. I'm an imaging scientist from UCL working on a collaborative project with the ESRF called the Human Organ Atlas, or the HOA. Today I'm going to tell you a little bit about the project, the data it's generating, and the ways in which we're making the data fair. Begin with a little bit of background on the problem. So in 2020, we all know what was going on. The COVID-19 pandemic was in full flow. And there are two medics from Germany, Dr. Max Ackermann and Dr. Danny Jonnek, who were trying to understand how this disease was impacting the lung microstructure in the patients that they were treating. Danny and Max got in contact with Professor Peter Lee from University College London and asked him if he knew of imaging techniques that could help image this damage in 3D with more context, more spatial context about the lung. Professor Peter Lee has worked with synchrotron and X-ray imaging for many, many years, and he knew that the European Synchrotron Radiation Facility had just recently finished its upgrade to being the first fourth-generation source in the world. So Peter Lee contacted Paul Taffero, who's the beamline scientist of one of the beamlines at ESRF, BM18, and asked him if he would be able to help. So what came out of this was a technique. The technique is called HIP-CT, Hierarchical Phase Contrast Tomography. Now, HIP-CT is a propagation-based phase contrast local tomography technique. Don't worry if you don't understand all of that. Essentially, we generate contrast in our imaging technique via having faint density differences in the sample, which create refractive indice changes, and these are the basis of our contrast mechanism. What HIP-CT allows us to do is to image whole intact human organs without sectioning them, and then to zoom in to regions of interest anywhere within the organ and scan these at high resolution. So we normally scan at three tiny levels of resolution. We have our whole organ at about 25 micrometers per voxel. We then scan a region of interest at sort of a middling resolution, which is about 6 micrometers per voxel. And then we go to high resolution, 1 to 2.5 micrometers per resolution. And with this protocol, we've shown previously that we can reach single cell resolution inside an intact human brain. So to do this, firstly, there's some sample preparation here. This is an ex vivo technique, so we're taking samples from organ donors, we're fixing them and we're preparing them for scanning. We're then performing our scanning. The scanning looks a little bit like this. So there you'll see a sample, a brain sample. It's being rotated. It's being scanned tomographically for the whole brain. We then select regions of interest within that organ to scan. So what this ends up looking like is a bit of this. So here, this is a data set of a COVID-19 lung lobe imaged by one of my colleagues, Joseph Brunet. Inside it, you can see the yellow and the green regions of interest. Those are our medium and our high resolution. These data sets are 3D, so you can see us here scanning through that data set. You can see the green region here, that higher resolution. You see how the data sets are perfectly registered to one another. You can see some of the damage in the lung, and here we're transitioning to that high resolution region of interest, the 2.5 micrometer. When this pauses, you'll be able to see some small flecks in places. We think these are individual cells. As we zoom back out, you see that you retain that hot context of the whole organ, and we can take as many of these regions of interest as we want. There are some caps on that, but we can take a lot of these different regions of interest within the entire organ. So what we have then is a technique that allows us to do this multi-resolution imaging across intact human organs. And what we realized very quickly was that we could apply this to the whole range of human organs. So we image at 3 resolutions. Our final images are all compressed in JPEG 2000, which is about a 10 times compression, but still we end up with these very, very large data sets. So our whole organs at our 25 micrometers are anywhere between 5 to 80 gigabytes. That's with the 10 times compression. We can have these medium resolution regions of interest, 20 to 100, and we can have the high resolution regions of interest, 1 to 2 micrometers, go anywhere up to 150 gig, depending on how long a column we want to image. And as I showed you, we can have multiple of these regions. So it's very easy, as you can imagine, to quickly get a multi-resolution data set of an organ that's larger than 1.5 terabytes. So it was a real challenge for us as to how we share this data, interact with this data with our collaborators. The project as a whole currently stands, we have over 23 institutions and 50 active collaborations worldwide, and this is growing every day. And you can see here some of the different groups that we collaborate with around the world. And this creates a challenge, trying to move this data is difficult, trying to ensure collaborators have access to the levels of data they want and can interact with it in meaningful ways. So we also consider the fact that we don't just have one type of collaborator, we have many different types. So we have a lot of the medics who we collaborate with, image analysts, biologists, medical illustrators, biophysicists, engineers, and all these people want to access and understand the data in slightly different ways and will have different resources available to them in terms of being able to handle the data and interact with it. So what we really wanted was to create a way that all our collaborators, but also anybody worldwide, could download this data and interact with it in as many meaningful ways as possible. So the project, in order to do this, we developed with the PaNOSC team from ESRF, the Human Organ Atlas. So it can be accessed at this website, and I'm going to do a little video demo of this now. So here we have the Human Organ Atlas, and if I just go into there, Human Organ Atlas at ESRF.eu, you'll see the front splash page that we have here. So this just gives you a general overview with our affiliations, a video of the brain, and a few other bits and pieces. I'm going to show you around it a little bit. So if we go up to the top here, we have the 3 tabs, Explore, Search, and Help. If I go into the Explore tab, you'll see how it's arranged. So firstly, we're arranged by patient or donor. Each of these represents a different patient from which we have samples. So if you click on one of them, you see the different organs that we have imaged, and you also get a bit of description about that patient. If I click on one of the others, you can see in this patient we just have the left lung. Here we have the brain and the kidney. If I go back to this patient and we look at one of the actual organ data sets. So if I click on that data set, on that organ, it shows all the data sets for that particular organ, so all those different resolutions. So here you can see we have quite a lot of data sets, some at the middle resolution, some at the lower resolution. For almost every organ, we always have a complete organ overview at that 25 micrometer data sets. So if I just look through the descriptions of the data sets here, you'll be able to find the one that says complete organ there. If I click on it, it takes us into the actual data set. So here we have on the right hand side just overview images to help people orient and understand. Sometimes there's videos. We also then have the description of the data set. We have that description about the patient as well. We have descriptions about the samples, and here we have all the scan parameters for the image acquisition, and at the bottom all the parameters for the processing. On the right hand side you have here the actual data sets that you can download. We provide them at different levels of binning to help people who don't have as much capacity for the full data sets. You can also download the metadata as a text file if you want. We also support at the very top there, you can see that you could download the files with Globus. This is really useful for those who can access it for a more robust, faster download. The other thing that we implemented was this search tab, which is quite cool. What it allows you to do, you can scroll through and search the data in various ways. So for instance here, I'm searching via age or sex. You can imagine as the Human Organ Atlas grows, how useful this kind of searchability will become if you want to only analyze specific portions of the data. You can also do this based on the scan parameters, so potentially for those who are more interested from the image acquisition, image analysis side of things, we have various scan parameters that you can filter the data by. And then we also have this quite cool bit in the middle whereby you can search by pathology. So for instance, if I type in COVID into here, it will pop up all our data sets that are associated with patients who had COVID. We can also search for different diseases. Already in the database we have quite a few things, so diabetes for instance. There's some organs there. If I click into one of these, this is the kidney for instance of a patient with diabetes. If I go back to the search again, can look for other things, something like cancer. So you can see as we get more and more types of pathology into the Organ Atlas, how useful this will become. We have, of course, a help tab just to help people navigate around the Organ Atlas. That was the Human Organ Atlas, and you can see how powerful it is. We're also doing a lot of exciting new things in the future. So we're going to be adding a lot more data to the Organ Atlas. Watch this space. We're going to be trying to decide how to get better representations of the fully registered multi-resolution data sets, and to do more automation of our metadata creation and our data ingestion, just to be able to avoid any potential errors. The other thing that I'm excited to preview and show you guys today is that we're using we're developing a web browser interactive cloud. So it's based on NeuroGlancer. So this here is just one of our data sets, and the NeuroGlancer interface allows 3D visualization through cloud stored data, so anybody can access this. We can also add annotations onto this. So here you can just see me adding some annotations for, I don't know, a blood clot or something like this. And you can add 3-dimensional and different shapes as your annotations. So this is really particularly powerful for a lot of our medical collaborators who perhaps don't have the infrastructure, the computational infrastructure to download and deal with these data sets, but nonetheless it's incredibly important for our project that we get their interaction on the data set. So like this, without downloading the data, just with any web browser, you can do this on a smartphone as well. You can go to the data, interact with the data, mark it up for us, and we can have interactions with people like this. So it's a really exciting new avenue that we're keen and excited to develop further. So just to say that all the videos and methods and the data, obviously, are publicly available. We have a YouTube channel as well for looking at some of these data, the Human Organ Atlas, and we have our website. And I just want to say a massive thank you to the whole team working on this project. It's a huge collaboratory effort, and we couldn't have done it without them. So thank you.